Okay, good um evening. Um so kind of funny. It's day 93. I was at my parents' house this morning. And I did start recording this video on my laptop. And well, first off, I was up at like 10 a.m. and I was like, I've really been liking my Debian Windows dual boot on this desktop. And so I was like, well, actually, originally I had a Kali and Windows dual boot on my laptop, but I never used Kali because I mean, I'll be honest, kind of hate it because I have no use for what Kali was made for, right? I don't know too in depth of what it was made for, but I know everyone says it's like a security operating system, or extension of Linux, and so. Um, And so, I installed that a while back, um, because of course, Mr. Robot, and he uses Kali Linux. That was actually the only distribution that I had ever seen of Linux at the time, last year, because I just did Windows all the time. And so, but then I never booted into it. I never had a use for it. Um, or it's not even that I need a use for it, but I should be familiar with the differences between Windows and Linux in terms of navigation and package management, different commands that are using, just at least surface level stuff. So usually it's like, if I'm playing a game or something like that, I'll be on Windows. If it's something that just if it's Windows specific, I'll go on Windows. But Linux, it's kind of just faster and more lightweight. I've come to find, in just being able to navigate around a terminal or a file system and stuff like that. So, um, as in literally like when I boot NeoVim in a terminal on Windows, it takes a few seconds. On here, it's instant. And so then just apply that to all like saves and going into files and like all of this and just interactions. It adds up and it just makes it a lot more fluid. Um, but um, but yeah, so what I was getting at was, so I woke up at like around 10 a.m. and I was like, okay, I'm gonna change the Kali to Debian, so that I can start using Debian on my laptop as my main kind of runner because I've been loving it on this PC. Um, and it took me like 3 hours to do, because first off, the install for some reason took a while. Um, I don't even think my network was like that bad at my house, but so the install took a while, and then when I messed up, like I was just trying to rewrite what was already partitioned for Kali, in my memory, and it like wasn't liking that, so um I had to clean I had to not only wipe that partition, but I also had to reformat that partition to just being labeled free space. So I had to boot back into an operating system that allowed me to get into terminal, which I mean I could have done, I'm pretty sure, within not BIOS, but whatever that Windows pre-boot, but it's fine. I could just boot into Windows, and then I had to look at like disk management stuff. Um, and then after I got that done, went through my Debian install, and then just needing, so many different packages, installing OBS, installing NeoVim. NeoVim was giving me problems, getting not only Zen and OBS as actual desktop files. Um, it's just so many things I had to do. So, yeah. Um, and then by that time, I was having dinner with my family, and um, oh my god, excuse me. Um, and so I ended up recording like 10 minutes of like an intro and a little bit of getting into the projects. And I was like, I don't know why I'm doing this right now. So here we are. Um, um, yeah. So there's one thing I did want to talk about. Um, even though again, I don't even think. no one really watches these, but I'll ramble to myself and maybe look back on it one day. Um, I was watching a podcast. I saw a recommended video a few days ago by Jim Keller, who's a I guess you could call him a computer architect. Um, works he worked at like AMD and Intel and um, a bunch of like digital and stuff like that, um, as a computer architect, and now he is the CEO of a company that is working on chips and also a part of or leading, I don't know, another company that is making affordable and I guess transportable, in the fact of, so like, if you have any familiarity with how chips are made, um it's it's not like something that it's like 3D printing, right? 3D printing, you can just throw something on the top of your shelf like this thing and then you can print out something. It's like, I mean, at least from what I remember when watching videos throughout the year of maybe some chip stuff, is it's like you have to be in like a white room. You have to make sure that you're on like level grounding, and it's like, no sort of vibration can happen like through the earth and stuff like it's so precise and it's so um materially materially demanding. As in like these machines are huge. It's all for just this like little 12-inch wafer to do what they do to it, to make all the um transistors and whatnot. But um so their idea is basically, I mean, how I understood it was make like the 3D printer of CPU design, right? And so it's like usually it's like if you define like an architecture for like a CPU, um, either most of the time if you want to test it, you have to go. I mean, there's no other way. You have to like reach out to one of these manufacturers, and you're probably gonna have to pay a pretty penny. I haven't looked at the prices, but I would assume, to just do a one-off of a chip design, and maybe, and for a lot of these places it's probably not about the money but about the time, like sending in the schematics and then you have to wait for them to get it, process it, you know put it in for a schedule, and then go through, make it, package it, ship it. That's weeks if not months to get just a prototype that could have just been broken, even though there is good simulation software, I'd assume it's just not good. Or by the time that month has passed, you're already at a new iteration, um, and it's just kind of obsolete. And so their whole thing was making like the 3D printer of CPU, manufacturing, um, and but anyways, I thought that was just cool, is what I was saying that. But he was talking about something I wanted to look into today actually as well, because I wanted to do branch prediction in our computer architecture for my class this semester. Is Number one, I don't really understand branch prediction. It's probably my the most lacking overall, like high abstraction concept that I like kind of, I understand like kind of like I mean the purpose is for efficiency, right? But I don't understand like how it's predicting. I mean, I assume it's just like, oh, we see this type of pattern, right? I mean, that's all it can really be, is a pattern. Or, oh, we've seen this sequence before, we're going to predict the rest of the sequence. But also, what is like a sequence? Is this like a branch prediction for opening a program? Like, oh, when we open the program, this one, and then this one, and then this one, and this one, let's predict that all of this now happens. And then how big is the I mean, I've heard my professor talk about like the penalty of faulty branch prediction. But what does this look like, especially as like a higher architecture? Is there multiple branches that are being predicted, and then it follows a lot of these? Like, I don't know. I want to look into that. But the big thing was, how just AI fits into computer architecture. Because when I think of computer architecture, I think of low level programming, hard coded, secure, reliable, stuff like that. And when I think of AI, I think of very, um, not reliable, very fun, very dynamic, but not precise. And I feel like computer architecture needs to be precise. And also putting in like an AI into, I feel like there's a lot of security risks in that. I feel like there can be, you know, I don't know. And so I want to look into that, like how, I mean, it's literally the Google that I have in now. I haven't looked at anything. Is, how does that fit into, because he was talking about how, like, at this point, CPU chips, just like how, like, NVIDIA is so, popular now because of the tensor stuff um, and whatnot. And it's all AI related. But he was like, CPUs now, like, this is where you get the performance. Like all architectures are very similar, and there's not much to improve, at least from what we can tell right now. He was like, but prediction, and getting a model that can really predict what the computer is going to be doing and can fetch accordingly ahead. That's where performance really will come from. And so I just want to kind of like look into like how this fits in and see if I can do anything in my project, which would be really cool. But I don't know how available this research is, what it entails, what the future looks like, what in the past. Um, are there chips out right now that have stuff embedded in them? I don't know. Um, and then the other thing I want to talk about, which is pretty scary, was him talking about, and I know there's so much like doom around AI, especially for software engineers, right? And so I didn't expect it from him because he's like been in the industry for 40, 50 years. Um, 40 years. I think he's like 60 something. Just calling it 50 would be a little whatever. So like 40, 45 years. And you would think he'd be seeing how, well, I don't even know because I mean, from the looks of it, right? Um, you look back 45 years and what? I don't think there's 1980s. What type of computers were there in the 1980s? It was, didn't the Apple II came out in the 80s, right? When did Apple come out? Wow, 77. Okay. So 45 years ago was around this time of, when did the Commodore come out? 82. Okay. Yeah, so around the time of the Commodore, and like, so very early computer, like the kind of like the dawn of like a personal computer is when he got an industry. So I mean, yeah, stuff moved fast, I guess. But not as fast as, so my whole thing is that he ended up saying, like, I think in 10 years from now, all software will be obsolete. No one except for like hobbyists will be writing software. It'll all be generated, you know. There is no future um of someone sitting down and writing, code for a company's tool. Um which, is sad. Um but I don't know if it's sad for the right reasons. I think it's sad for just the reason of like me being unemployed, right? Like outside of that, it's like, I mean, outside of that, and also the kind of the beauty of it, I think programming is really cool, and like the whole, um, just the whole idea of like, you know, looking back like 60, 70 years, and within a lifetime of people that are alive right now, to go from pretty much nothing in computing, or yeah, nothing in computing outside of literal mathematic, hard mechanical computing, right? Like the Enigma for World War II, um, and stuff like that, right? Um, to go from something like that and that being the most breakthrough thing to like, you look at today, oh my God, like technology is crazy now. Um, you know, uh, yeah. Um, and so I just think it's cool of like how all that has been built traditionally. And that's what I really like about it is it's all just like, all of this stuff is just hunks of metal and wires, but the reason they perform how they do is because of, you know, what software engineers write. Um, and so the idea of that just going away, um, is sad in the selfish reason of, got to find a new job, and it'll only be hobby at that point. And this is all saying like his prediction is true, right? Um, because I'm sure there's a bunch of other professionals who have been doing this for 40 years that say no way. Now I do think I don't know. It really depends, uh, um, because it just depends on a lot of because obviously industry moves really slow, right? Um, Especially at like the top level, like the big giants of tech, right? When something new comes along, it's gonna take years for them to transition to it. I mean, something like a startup can pick it up like that because all you have is, I mean, you have nothing, right? And you only have like a few people working on it. And so for people to learn it and incorporate it, it just is like that. When you have tens of thousands of people in existing projects that are hundreds of thousands and millions of lines, to incorporate something new um, is not easy at all, right? It would have to be something world altering, which, you know, because it's like you walk around now and it's like how much AI do you really come, in contact with? And it's like, okay, websites, right? Chatbots and stuff like that has been around for a while, but they're, smarter now, can help you more outside of direct LLM use, right? It's like algorithms, right? For social media. You step outside of technology in like general and walk outside, there's nothing. All there is cars. I mean, that's still technology, right? So I don't know. It's not like even with like the big boom recently, it's not like unless you're really tapped in, it's not like it's changing your life. The biggest change has been large language models and just going to a website and being able to type in and get no matter what, getting an answer back. It could be wrong, could be hallucinated, um, but yeah. So yeah, it's just a little scary to think about, I guess. But yeah, yeah, I don't know. It was just a little shocking to hear, especially from someone like that. But I've been liking listening to that guy. I'm smart guy, and because this whole semester really is going to be about computer architecture for the most part. It's nice to listen to people who are in industry and what they have to say. So yeah. Anyways, um, plan for today. I don't know how long I'll record. It'll probably be at least an hour, but I don't know outside of that. I want to work on just the computer architecture code. Um, that's about it. Maybe a leak code and computer architecture code. As for the computer architecture code, I still want to outline, make sure I have everything for DRAM. And then, you know, I think it'd be nice today if I could. Oh, yeah. One part of the thing I recorded earlier today that I not ending up using the recording footage is the idea of making an instance of memory, right? I was like, how are we going to access like this memory? And I think it's going to be something where we define a, I don't know if it's going to be like a type or something, but we have like a memory thing that is a pointer, right? We call the function that initializes the memory at this variable pointer. And then when I go to a write to memory, I reference this pointer of the memory instance that we created, and it puts it within, like if we specify an address of, I don't know, 44, it goes to the 44th spot in the array, um, and just inserts it into there. And then if we read from that address, it'll just give us back that. So, um, So yeah, if I could just get that rocking today, that would be perfect. But we got a lot of C syntax to figure out because I am not good with C. So that, and I also want to do the research on the AI and computer architecture. So I'm gonna pause for 1 second and then we'll get started. Okay, so I wanted to look at what role does allows them to brainstorm their ideas. Oh hell nah. How long ago was this? Uh oh, IBM. I love IBM. When was this? God, I hate having to scroll to find when this was posted. Or you just don't tell me. Okay. Oh, 2024. Okay. Nope, not you. Artificial intelligence computing is the process of scouring volumes of data for insights into capabilities with the use of machine learning software and tools. The process, which is critical to many cutting-edge technologies like generative AI, edge computing, and the Internet of Things, relies on development of AI models through. AI helps automate routine and repetitive tasks, increasing give me wiki branch prediction. Wow, that's definitely how you spell that. Oh my god, I keep misclicking. 1 second. Crap. Computer architecture a branch predictor is the digital circuit that tries to guess the way a branch will go before this is known. The purpose of branch predictor is to improve the flow of the instruction pipeline. Branch predictors play a critical role in achieving high performance. Two-way branching is usually implemented with a conditional jump instruction. A conditional jump can either be taken and jump to a different place in the program's memory, or it can be not taken and continue execution immediately after the conditional jump. It is not known for certain whether a conditional jump will be taken or not until the condition has been calculated. The conditional jump has passed. Okay. Without branch, without branch prediction, the processor would have to wait until the conditional instruction has passed execution stage before the next instruction be fetched. Branch predictor attempts to avoid this waste of time by trying to guess whether the conditional jump is most likely to be taken or not taken. The branch that is guessed. Okay. Time that is wasted on a branch mixture is equal to the number of stages in the pipeline from the fetch stage to the execute stage. Modern microprocessors tend to have quite long pipelines that misprediction delay is between 10 and 20 clock cycles. As a result, making a pipeline longer increases the need for more advanced branch predictors. The first time a conditional jump instruction is encountered, there's not much information to base a prediction on, but the branch predictor keeps records on whether branches are taken or not when it's encountered a conditional jump. Okay, branch prediction is not the same as uh, branch prediction attempts to guess whether a conditional jump is taken or not. Okay, static branch prediction. Static prediction is the simplest branch prediction technique because it does not rely on information about dynamic history. Instead, it predicts the number of a branch based solely on the branch instruction. The early implementations of MIPS to first risk architectures use single direction static branch prediction. They always predict that a conditional jump will not be taken, so they always fetch the next sequence. Only when the branch or jump is evaluated and found to be taken does the instruction pointer get set to the non-sequential address. Both CPUs evaluate branches in the decode stage and have a single cycle fetch instruction. As a result, the branch target is 2 seconds long, and the machine always fetches. Okay, a more advanced form of static prediction presumes the backward taken, a forward branch will not. A backward branch is one that has a target address that is lower than its own address. This technique can be helped with prediction accuracy of loops, which, okay, some processors allow branch prediction hints to be inserted into the code to tell whether the static should be taken or not. The Intel Pentium 4 accepts branch prediction hints, but this feature was abandoned later. Okay. Static prediction is used as a fallback technique in some processors with dynamic branch, blah, 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 blah. Yeah, dynamic branch prediction uses information about taken or not taken branches gathered at runtime to predict. Okay. Random branch prediction. Using random or pseudo-random bit, a pure guess would guarantee every branch a 50% correct rate, which cannot be improved or worsened by reordering instructions. Also, it would make timing. Okay. Next line prediction. Some superscalar processors fetch each line of instructions with a pointer to the next line. This next line predictor handles branch target prediction as well as predict. Such branch itself will generally not be the last. A 1-bit saturating counter records the last outcome of the branch. This is the most simple version of a dynamic branch predictor possible, although it's not very accurate. A 2-bit saturating corner is a state machine with 4 states. Strongly not taken, weakly not taken, weakly taken, strongly taken. Okay. When a branch is evaluated, uh, branch is evaluated as not taken, change the state towards strongly not taken, and branch is evaluated as taken. Okay. Okay. So the whole thing is literally just, it's not actually like predicting. It's just, mm, I guess what's a prediction then? Interesting. Why not? I mean, the whole point of the branch prediction is so it can go through. Uh, so does hold on here. Does a So my whole thing is like, right, is what you do is you fetch an instruction, and that instruction, once it starts decoding, you fetch the next instruction, and it just keeps going like this and this and this and this. So my thing is what is the okay, I know that, but oh, I guess so, yeah. Because like, I mean, it's only a few cycles though, right? Like we're talking like if we want to see if these two registers are equal to each other, right? Then take this branch, right? Um, so I mean, both those instructions have to go through the pipeline. So what? It would be like six clock cycles to figure out. Um, whoa. It would take like six clock cycles to. Sorry. Um, right. So blah 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 blah. Uh, I see. Okay, so the whole thing is you go in, you're doing this, this, this. You hit a branch, it goes from execute and then it goes to decode. Now the next instruction, 2 bytes away, because we're doing word addressing, gets put into the pipeline, right? Right. And as this shifts, once we get to a write back, right, this says, oh, we do need to take this branch, flush the pipeline, because we don't care about anything and we don't want to write anything because you know, we don't know what this branch is going to give us. So the whole pipeline needs to be flushed, and then it needs to change the program counter to that address instead of return address to back to right after that branch. Do the branching and then go back to that. So with the branch prediction, if it takes the branch successfully, it means that it was already taking in instructions in the branch by the time it was resolved. instead of going to the next stuff after the branch. And so, yeah, I guess it's either way. So, I mean, this way it's possible that, because if you never did branching, right, every single time you hit a branch, right, a conditional branch, I should say, right, it's 100%, not 100%, but it's at least going to be wrong, sometimes, right? And so, what if you could improve that? That's like what a branch predictor is. Okay. Okay. Yeah. So, how could AI go into that? I mean, hmm, that is a question. How could AI go into that? Interesting. Okay. So, enough of that. Let's. Let's go to CD desktop. Is that what I want? Yeah, CD database. Coding CIS. Uh, Neovim. You know what? Give me get status. Really? Oh. Oh, okay. So let's. Here, actually, let me just do that, and then go to github.com. Go to ISA architecture. And actually, what I need to do is I need to create some issues. So, what was my teammate doing? Toy set associative. Okay. Um, I need to message my teammate real quick. Carried away, looking at some stuff. And messaging my teammate. Okay. So need to make a main memory pointer. So we initialize simulator. Um, can be disabled. For testing slash efficiency. And let's be honest, in an actual CPU, the cache is just made for efficiency. In a simulated thing, we can just turn the cache off and have the cycle time set to fucking 1 on DRAM. And that way, when we're testing the pipeline, we can just instantly get feedback on a write or a read. Um, so let's do that. Um, so we have a main memory reference, um, DRAM read and write. Um, Is there any time I'm dealing with anything but an immediate? I don't think so. I mean our word size is 16-bit, right? So I'm storing 16-bit stuff for addresses, right? Or for data in memory addresses. So I'm just storing either a immediate value or an instruction, right? I'll just do this for now. Okay, so that's DRAM read and write. Um, is there anything I am missing here? Oh, I never even cloned this yet. But initializing, reading and writing, clearing and display. I think that's all I need right now. Um, Actually, first I need to do a git status, git checkout DRAM, and then that's kind of fun. Oh shit! What did I do? Okay. Well, I'll do that again, and just make sure. Yeah. Okay, we're good. We are good. Okay. Okay, so for testing right now, I'll just do this on 10 cycles. Um, so how I saw this, what was this I was looking at earlier? Trace-based simulator. Well, anyways, I think for this, what I want is so in C, right? A C function expects a return type, right? Right. What are you going to be returning? Is it an integer? Is it nothing? So I'd assume something that would be nice would be to do define our types. So if I have a type definition for um what will it be? Not the DRAM size, but the actual like how oh wait, I have it right here. Type def integer. But what if I want to make just my own type? Because what do I want? I want just an array of 60,000 things, right? Whatever. Struct, which is a pointer to memory. Or it's a memory pointer. See, I don't understand. Oh, elements in size of. So we have this many elements in the size per each. Okay, sure, sure. I mean, so it's a type definition structure that is formatted into a 16-bit integer, and we're calling it memory. Honestly, I'm just gonna call it a static DRAM size for now, and we call this type just DRAM, right? Um, so to simulate memory, what? So this would be a. We're gonna return. Ooh, what are we gonna return? Okay, so it's returning nothing, and we're giving it the type of DRAM with a a parameter of type DRAM with a DRAM, and we're saying okay, the in the structure our DRAM value, the memory value is equal to a calc of the DRAM size. But okay, in this scenario, I wouldn't have to do this because this is static. So, but it's like in I mean, I like the calc thing and then the size of a 16-bit, but I guess I still just don't understand the structure. So I have a typed up structure called DRAM. Like, why not just call this, get rid of this, and just say memory is equal to a calc of the DRAM size times the size of this, right? I mean, what's wrong with that? And then down here it would be what I say. I mean, it would just be a call to init DRAM, right? And so what am I passing through? Well, like right here, why am I passing through a DRAM variable? If you look at the initialization, we're just doing a pointer to, I mean, honestly, just this memory, right? Because here I'm doing DRAM, and at this with the address of DRAM, and then this is the pointer to DRAM, and then DRAM is this. But if I don't pass anything through this, and I just say memory is equal to this, I guess that's the thing though, is it's not like global anymore. Because like here I could just reference. So I guess it is like I do want I do want this, right? And so I will pass through a DRAM thing into here, and so this will go to that. But I still am doing this with a hard size. But if I'm doing this with a hard size, why even the need for this, right? Right. So this honestly just is working as a, you know, doing the pointer, but it's like so the whole thing of doing this though is that now the memory that I pass in, or yeah, the because down here what happens is I no longer want this, but it's just going to be I have a init, or no, I want to make a DRAM type, and it says the address of DRAM. So I mean, when I do this, right, when I make a DRAM type, and I get the address of DRAM, it's because, well, technically it's because I'm allocating space on my computer for the simulator, and this is an address on my computer, right, for DRAM. So it knows, you know, where to reference from. So then when I call, to initialize the DRAM, and I just pass through this as the parameter, and then sets the memory size to DRAM size times the size of the unit. Again, though, I don't. Okay, this is the okay. For now, I think I literally just do this, and I say fuck you, right? And then here I just say DRAM, DRAM, right? And then technically, I'm pretty sure if I do a print f of this, and this will have what percent d this, and then I do the address. None of those are address. The address of DRAM, right? And then oh, is it just GCC? What is it? I don't think that. I think I could just do GCC. I think I can just do this. Oh, oh, do you actually want that? Oh, right here. I don't know how they did it up here. Oh, DRAM is just this. I guess it would be weird to initialize something as its address, right? You would initialize it and then reference the address. Um, Beautiful. Okay. Okay. Can I print out the size of? Did I even save this? Beautiful. Beautiful. Okay. So now, like I said, this is subject to some change. Let me choose this. It's subject to change because I mean, like, yeah, memory management is cool and all, but this is all just this is all proof of concept. Okay, okay. Let me see now. Not using any of this stuff. Wonder how much Wikipedia stuff there is like on these topics. Wow, I cannot see a single search. Um, okay. Function to write into address. So we have our DRAM that we reference, and so we want a function that will say, I mean, DRAM right now is just simply a, well, what do we want to return? We want to return, we want to write an immediate to a particular address, right? So we want something that is returning. I mean, can you have this as a return type? Oh, I hate that sound. What do you mean? Okay, I don't know if you can have. Let's just try. Let's say this is our return type and we have a write to memory function. I want this to take in the DRAM. Um, it's going to reference our DRAM. It's going to reference. What else do we want? Obviously, we want immediate value um, and an address. So we want the address and the immediate, right? Oh, all these need types. I forgot this is. Um, so the address is just an integer. Um, int, yeah. Integer and an integer, I guess, for now. Um, so what you want this to do, I mean, I guess in the simplest way, you just want to do a check for, I mean, what's the actual like address? I guess for now I can just say if the address is if this is less than the address and the address is less than the size of DRAM, right? Then I can say DRAM at address equals the immediate. And okay, so this would just be void because all it's doing is writing to that, I think. And so if I initialize this and then I say write to memory with um, with the address to DRAM, um, space 50 with the value of 78, right? And then I said printf memory in DRAM insert, which will also just be a decimal type on a new line. And so I want to print off DRAM at 50. Let's see what errors we get. I just did it twice. Oh. Do DRAM at memory address. Hmm. So instead I should check if the address is greater than or equal to 0 and the address is less than just DRAM size. Okay. Well, okay, sure. Scripted value is neither. Okay, so it doesn't like. So what? I want to say DRAM at memory 50. No, it does not. DRAM dot memory. Okay, that makes sense. That makes sense. Okay. Um. if before this says it, what would I do without hard coding it? There has to be like a simple two binary thing. I feel like. Okay, yeah. Just a simple cast to uh, uh a uint 16t. I don't know that's how you but do I want to do wait, let's think about this for a second. What am I trying to do right now? I'm trying to write the memory system this is all going to build upon, right? So how are we writing stuff? We're writing stuff with as in an address space, right? So when I fetch from an address, right, the easiest way is it for it to be a binary, right, that I get back. Like this is the immediate binary value. This is the immediate binary value. Add these values, right? I mean, I guess because it's a simulator, it's not that, right? Like okay. When I end up writing the instruction in coding, it's going to if I say store value, right? A store right into memory at this address, this value. What is it going to do it in? It's going to do it in binary, right? So like eventually I'm working on the instruction set that'll be all the instructions. And those instructions are going to have to use this memory system. Right now I'm just testing it right here. But what is a write to memory going to expect on a well, I guess we have the assembler, right? Which is going to take our assembly code and put it to binary, right? So I guess the thing is when it goes and it fetches the next instruction, right? And the assembler decodes it into our binary encoding, right? This is what this is expecting. It's going to be expecting those encodings, right? The only time assembly is actually being used. What is my we have when I want to store something, we have a 4-bit and yeah, an 8-bit immediate. I'll be right back real quick. I'm back. Sorry. I'm gonna end this video soon. Once I can just figure out what I'm trying to do here. Oh, okay. Wait. I'm low key. Well, no, I'm trying to think because like obviously in the instruction I just can define 72 as the immediate, right? And so when it goes to the assembler though, hmm. So the immediate coming in is going to be uint 16t. It's kind of what we're honestly. I'll call this the data. Um, so if I did something like this, oh, still says 78. I think it's like right into 50, right in. Right, it'd be some shit like this. 72. Oh, you think this needs to be like a B? No. But so I can pass in just 874 and this works just fine. Okay. So is it literally we have an instruction, right? That like let's say we load into memory. I guess that is interesting, right? Because we're never actually doing a call to load in a 16-bit instruction into memory. I mean, if we were, technically what you could do is you could say, no, okay, I think I know. So, and now to read from this, it's just going to be, I mean, are we returning something actually here? I want it to be um, right? And so then to read from an address, right? I don't care about, I just care about the memory and the address. And I say, well, as long as the address is valid again, I want to return I want to return this, right? So it's going to be if then um well, we actually this is a pointer reference, so I still want to do um DRAM, but no. I want to say um return value is equal to DRAM dot, or actually because this is a reference, it would be this, right? Let's try this and then we do a return. Um, return value. And then this is not a write to memory. This is a read from memory. And so then instead of this, result is equal to a read from memory of the address of DRAM and the immediate of 50 printf value at memory address. Result undeclared. Oh, sorry. This is a oh 874 and 12 hundo. Beautiful. Make sure that this is just working. Amazing. I don't need to um okay. And then this is the whole thing of while delay. Sorry. This is a while wait. Why was this writing then? Oh, hold on. Sorry. All right. Yo, can I type? Wow. That's actually kind of crazy that this actually works. While delay, but when delay hits zero, like I'm able to just Oh, you know what'd be cool? It'd be cool if I wonder. Wait, I want to see this first. Okay, I don't actually care about this. Okay, that is fine by me. Um, I also do wonder though. Okay, so it's saying if I were to, instead of define this, just say int DRAM delay. But I'd have to do this inside like main, right? Yeah, no, I don't want that. Yeah, just make a local copy. This is probably just the best. Okay, make sure we're good still. Beautiful. Okay. Um, okay, let's push these changes to get status. One second while I get that key. Okay, I got that key. And so we should be DRAM, simulator, memory. Very good. Ah, a lot can be cleaned up here probably, and I still need to figure out if this is the right approach, but I mean it's something right now. Um, yeah. Wonder if my partner's done anything yet. No, it doesn't look like it. Okay. Um, what am I spelling wrong here? OOACH. Okay. Beautiful. Okay, that's about it for me today. Um, yeah. Um, I don't know. I feel like that use of ChatGPT is really nice. Like I understand everything about what I just did, right? And it was much more efficient than scraping through documents and old pieces of code and trying to piece stuff together. I'm sure, but if I did it that way, I would have more context and um, I guess more problem solving ability, but it would be taking me hours upon hours upon hours to do what I just did. Um, so I guess it is just kind of like a pick and choose of do you want to spend more time to possibly maybe get a little more knowledge, um, or do you want kind of more efficiency of getting right to it? And I think that's just something we have to play around with in the next couple of weeks. But but yeah, I think my C is very rusty. And once I get more, I have a hang for C and more of an idea of how I want to approach this project, I can kind of lay off, using generative AI and just kind of flesh out my own ideas and then just check it against ChatGPT. So yeah. Um, anyways, just Sunday night. I have class computer architecture in the morning, so I actually have to do reading that I just remembered for that class tomorrow, and then I have an exam on Tuesday. So tomorrow will be a short one, probably just delete code tomorrow. Because like I said, I have three classes tomorrow, And then on top of those three classes, most of the day is just going to be studying linear algebra. Tomorrow's a linear algebra day, and then Tuesday is a linear algebra day. Um, and then after that, it'll be right back to computer architecture and my 2:30 class, computer system principles, which are just neck and neck. So as long as I'm putting time into one of them, I should be pretty caught up in the other, which is nice. But yeah, um, yeah, that's all I got for today. I will be back for day 94 tomorrow, approaching day 100, end of the week, next weekend, well, this coming weekend. So yeah, take care. Bye.